Modern artificial intelligence assumes endless scale. We train models by brute forcing massive parameter expansion, allowing artificial neural networks to multiply without limits. This lack of limitation leads to a structural inefficiency known as digital obesity. Without physical or metabolic pressure to conserve resources, models accumulate redundant parameters. Over time, these bloated networks stop generalizing. The parameters begin acting as high-capacity memory banks, storing exact copies of training data rather than developing logic. In the physical world, living biological organisms do not have the luxury of infinite space or infinite food. But current massive server farms operate entirely outside the strict metabolic constraints that govern biological life. As long as we evaluate the success of an artificial intelligence by its sheer parameter count, we are engineering massive databases, not intelligence. The ultimate benchmark for computational efficiency is the human brain. It performs complex, generalized reasoning on a strict metabolic budget of approximately 20 watts. Biology achieves this through a specific principle. Comprehension is compression. Intelligence is the ability to form compact representations by identifying and exploiting patterns. A new theoretical framework proposes a spatial solution to replicate this density in AI. It is called infinite fractal descent. To force this architecture to compress information, the framework pairs it with a temporal training regimen called oscillatory hormesis, a process of deliberate computational starvation. To achieve biological-level intelligence, we must stop feeding neural networks infinite compute. We must start treating them as biological organisms subjected to metabolic pressure. The first step in eliminating digital obesity is spatial. We abandon massive, static, two-dimensional matrices, shrinking a whole layer to a single dense point. Infinite fractal descent defines a neural layer not by massive parameter counts, but by this high-density seed and a recursive transformation rule. Using Kronecker product expansion, the seed captures hierarchical relationships, embedding complex patterns with a significantly lower computational footprint. But perfect repetition is redundant. The math introduces metabolic constraint variables, forcing local variance and preventing the fractal from copying itself into total redundancy. This specific type of recursive weight sharing relies on K-FAC-reduce optimization methods, which calculate approximate curvature to train these structures highly efficiently. We no longer measure layer size by counting nodes. Instead, we quantify the complexity of this new architecture using a metric called the similarity dimension. These fractal layers use recursive, multi-scale connectivity to create short-circuit pathways for information. This structure allows gradients to bypass the deep layers that typically throttle them, preventing the signal from vanishing as the network gets deeper. By replacing massive flat grids with recursive mathematical fractals, we embed high-dimensional spatiotemporal information into a radically smaller physical space. Building a perfectly compressed spatial architecture means nothing if the network isn't strictly forced to use that tight space. Left alone, it will still try to operate lazily. This is where we apply oscillatory hormesis. In biology, hormesis is a mechanism where small doses of stress stimulate adaptive, highly efficient responses. This graph maps biological stress to computational training, hunting for the hormetic zone, where stress forces compression without causing failure. It locates the threshold dose, the exact tipping point of functional collapse. To enforce this, we mathematically alter the loss function, injecting an emergent metabolic penalty. Inspired by Poisson variational autoencoders, this penalty directly punishes high baseline activity. If a node fires too often, it costs the network. By mathematically starving the network, we leave it no choice. It has to abandon lazy data memorization for hyper-efficient abstraction. The network experiences this hormetic stress through a simulated circadian rhythm called the 24-hour metabolic cycle, executed in 4 discrete phases. Phase 1 is the squeeze. Here, the network's compute power and bit precision are drastically throttled. The system is intentionally starved of information. Look at this descending curve. It dictates a cubic sparsity schedule. During the starvation period, it progressively identifies and weakens low-importance connections throughout the model. This brutal pruning process forces the network to rely entirely on the underlying mathematical logic of its core fractal seeds. Then comes phase 2, the descent. The starvation ends, and full computational precision is restored. With its resources returned, the surviving, highly optimized fractal seeds are allowed to recursively unfold, mathematically expanding to explore wider potential solutions. This oscillation prevents the network from settling into the sharp, narrow minima that often cause overfitting. By forcing the surviving seeds to unfold and restabilize, the model lands in wider, more robust mathematical valleys that generalize better to new data. Phase 3 is the pulse, a dedicated period of rapid, calculated instability. During the pulse, the system is shocked by rapid oscillations in precision. This vibration prevents weights from settling and crystallizing into lazy, inefficient local minima. This stage leverages quantization-aware training. By embracing this chaotic oscillation, the model captures beneficial effects while avoiding the side effects of static low-bit representations. The cycle concludes with phase 4, consolidation. This phase mimics how microglia cells execute synaptic pruning in biological brains. The algorithm applies the metabolic rent law. Every neuron's cost is strictly calculated by multiplying its long-term traffic by its fan-out connections. If this cost exceeds the network's global energy budget, the connection is instantly killed, reallocating its resources to more efficient paths. Under the metabolic rent law, if a connection cannot strictly justify its cost, it dies. Only the most vital pathways survive the cycle. To properly evaluate these tightly packed architectures, the AI industry must move away from raw accuracy as its primary metric. We propose a new standard, the Metabolic Fitness Score. This formula evaluates a model by calculating its accuracy and sparsity directly against its actual physical energy footprint. For real-world deployment, the critical benchmarks must become accuracy per joule and F1 per joule. When graded on joule-based metrics, the extreme compression of an infinite fractal descent model maintains equal capability at a fraction of the traditional power footprint. A model's value is defined by its information density, the amount of logic it can extract from each joule of energy. The ultimate realization of infinite fractal descent lies in escaping traditional GPUs entirely and moving to Kronecker product logarithmic neural networks. This hardware operates entirely in the logarithmic number system. It takes the heavy matrix multiplications that drag down traditional AI and turns them into cheap exponent additions. By running fractal architectures on specialized logarithmic hardware, we finally eliminate the massive energy cost of matrix multiplication. We are transitioning away from treating neural networks as static databases and engineering them as simulated biological organisms. In synthetic intelligence, just as in biology, extreme constraint and starvation are the primary engines for achieving biological-level information density.